Okay, so we were looking at the hydrogen atom. Now what we had seen was, okay, there are not just one as in the Bohr model, but 3 quantum numbers that we need to specify to know what state the electron is. N is the principal quantum number. And it determines the energies of the electron. L is called the orbital quantum number. And the angular momentum of the electron around the nucleus can only take discrete values, which are given by determined by this L quantum number, and there is also the magnetic quantum number, sometimes denoted by ML. Now, N takes values from 0, 1 to infinity. L takes values from, N takes values from 1 to infinity. L takes values from 0 to n minus 1. And this ML takes values from 0 to plus minus 1 up to plus minus L. And the ML basically determines the Z component of the angular momentum, which is given by ML times h bar. And then finally, we said that the cosine of the angle that the angular momentum makes with the vertical, it cannot have any value, but only discrete values. Cosine theta given by Lz divided by L can only take values ML divided by L plus 1. Which is also sometimes called the space quantization. And then we were also, the last thing we had discussed was, the fact that Lz cannot be, that L cannot be in the direction of Z axis or any given axis. You see, if Lz was equal to L, then we knew that there was an axis such that the angular momentum is along that axis. It only has the Z component and it doesn't have any X and Y components. But the fact that Lz is less than L means that the angular momentum is not really, it doesn't have an axis. And this is consistent with the uncertainty relation. Delta X, delta P should be larger than or equal to h bar over 2, basically because if the angular momentum direction was fixed somehow, due to angular momentum conservation, we knew that the electron should be moving in a plane only. So we definitely know the position of the angular momentum in the perpendicular direction, in the perpendicular dimension. And furthermore, we knew the momentum in that direction to be 0. So there is no uncertainty in its momentum in that perpendicular direction and no uncertainty in the position in that perpendicular dimension. And hence, it would violate the the momentum position uncertainty relation. So, but there is no such problem. Now, any questions up to here? So, you see, the magnitude of L is given by Lx squared plus Ly squared plus Lz squared, right? Which is, no, you see, which is always larger than or equal to Lz. You see, the electron definitely has an Lz. It definitely has a magnitude. So if Lz was equal to L, that would tell us that angular momentum is in the Z direction, and we know its magnitude. Everything is fixed. L is fixed. But since Lz is less than L, it means that Lx and Ly are non-zero. So without knowing Lx and Ly, we cannot determine the angular momentum. And the uncertainty relation tells us that, I mean, we didn't see that uncertainty relation, but the uncertainty relation actually tells us that we cannot really know Lx, Ly, and Lz all at the same time. What is the uncertainty principle? No, that is the uncertainty principle we have. We cannot determine the momentum in an axis along a direction and the position along that direction simultaneously. That is the uncertainty relation we have. You see, we can know the position of a particle along an axis. It doesn't violate the uncertainty relation. We can know the momentum along an axis. Again, it doesn't violate the uncertainty relation. We cannot know both of them. So here we know the z component of angular momentum. There's no problem with that. Well, there is an uncertainty relation with the phi coordinate. We don't know that. You see, if you know Lz, then we know how the wave function depends on the phi coordinate. It's just its absolute value is just a constant. There is no preferred phi direction. So there is this uncertainty with Lz. Well, it depends on what you, I mean, you can say both. It is at all phi coordinates or it's at none of the phi. It doesn't have a phi coordinate. The probability of observing the particle in this phi direction is the same as the probability of observing it in that phi direction. Yes. Well, you see, when you are saying that the angular momentum constantly changes, you are implicitly assuming that it has an angular momentum, which changes. It cannot be. No, it can never be. What I'm saying there was, if it were possible to have Lz is equal to L, then we know definitely what the angular momentum vector is. But it never happens. Now, any questions on these quantum numbers? Okay, now let's try to understand what happens during transitions. In the Bohr model, the Bohr postulated that the photon was emitted when there was a transition. So E1 over n final squared was equal to E1 over n initial squared plus, n initial squared, the initial energy was the final energy of the electron plus the energy of the photon. So we could determine what the possible frequencies were. But this is kind of a postulate. Let's see how this relation comes from the quantum mechanics. Now, classically, we know that a photon electromagnetic radiation will be emitted if you have accelerating charges. Now, let's study what is the position of the electron. How does the position of the electron changes in various quantum states? Well, we cannot talk about the exact position, but we can talk about the expectation value of the position. So let's start with assuming that psi is equal to some energy eigenstate. Then we know how it changes with time. This should be an IR. It's an energy eigenstate, so it has minus I over h bar E n I times t. This is the time-dependent wave function. Well, what about the expectation value of the, let's say, the x component of the electron, the position of the electron? This will be integral over all volume, psi star RT x psi RT over the volume psi Ni R x times psi Ni R. Well, the exponential, the time-dependent exponential, they just cancel. So the average position of the electron would be independent of time. So it's not accelerating nothing. And hence it doesn't radiate if it's then in an energy eigenstate. Well, let's see. Let's assume that it makes a transition from an initial state to the final state. During this transition, the wave function of the electron will have this form. It will have a finite sum probability of being in the initial state during the transition, while the energy dependence is and plus some other probability to be in the final state. This will be my wave function during the transition. Now let's look at the expectation value of the position of the electron during the transition. Well, the definition of the expectation value is always the same. So it's psi star RT x psi of RT dV A star psi star R e to power plus I over h bar, this exponential, plus the second term, the position operator times A psi Ni of R is minus I over h bar E Ni of t plus B well, the rest is just multiplication. We should multiply this term with this one. But you see this, the exponential just cancel. There's a time independent, that's a time independent term. That's a squared psi Ni squared x. There is the product of the b terms. Again, the exponential will just cancel. But the interesting thing is the cross terms. You see, I will get this term multiplied with this term plus this term multiplied with the other term, and that would just give me twice the real part of A star B psi Ni star psi Nf e to power I over h bar ENI minus ENF of t. Well, let me just make some definitions. So let me call all this, the first line, it's just a time-independent constant. Let me just call it A. Let me call this integral no, they're not. Hmm? Yeah, I mean, I'm multiplying this one with this term, plus this term with this term, but the product of this term is just the complex conjugate of the product of these two. So I'm just summing a complex number with its complex conjugate. That just gives me the real part of, A star B and A B star have the same real part. They are just the complex conjugates of each other. So they have the same real part, opposite imaginary parts. Let me just call all this number to be capital B e to power I delta. It's a complex number. So the expectation value of x becomes A plus twice the real part twice B times the real part of e to power I over h bar ENI minus ENF t plus delta, or A plus twice B times cosine of h nu plus delta, where h nu is sorry, 2 pi nu t times delta. Okay, so what's going on? We have calculated the expectation value, and we have seen that the expectation value during the transition, the expectation value of the position of the electron, is actually oscillating. So what classical physics tells us is that if you have an accelerated motion, well, this is an accelerated motion in terms of expectation value. So if you have an accelerated charge, it will oscillate, it will emit radiation with the frequency equal to the frequency of oscillation, nu.
How come we have an oscillation if it doesn't depend on time?
No, you see, this depends on time. You see, what we looked at, we first looked at an electron that is not making a transition. It's in an energy state. It's in this state. It's not making a transition. Well, its expectation value of the position of the electron is independent of time. So no electromagnetic radiation. When it is making a transition from Ni to Nf, from the initial state to the final state, its wave function will be given by something like this. Then we looked at the expectation value of the position for that state. And the expectation value of the position for this state, which is the state during the transition, does oscillate. You see, this is the expectation value. A and B are just some real numbers. They are constants, but we have this term. So it's oscillating, which means it's accelerating, and hence it is emitting electromagnetic radiation. It is. What do you mean why it doesn't fall? Well, let's see. It makes a transition from the initial state to a final state. Both states should exist. There is a minimum possible energy state. It cannot go below that energy. So that NF, the smallest possible value of NF is 1. And when it is at 1, it just stays there. It cannot make any other transition. There is no other state for it to go. That is why it doesn't radiate anymore once it reaches the ground state. Yes. You see, this is no transition. When there is no transition. And this is when this is the during transition. So when there is no transition, it doesn't emit, basically because the expectation value of the position of the electron is fixed. When during transition, it emits an electromagnetic radiation because essentially the expectation value of the position is oscillating with the frequency of the emitted photon. Well, it depends on what the final is. For example, if it starts from the n equals to 5 state and makes a transition to the n is equal to 3 state, it will emit a photon, but it cannot stop at the n equal to 3 state. Within a very short amount of time, it will decay into an n is equal to 2 or n is equal to 1 state. But once it reaches the n is equal to 1 state, which is the state with minimum possible energy, it just cannot go down. There is nowhere to go. And when it is in that state, since it cannot make any more transition, why doesn't it emit electromagnetic radiation? Well, because its expectation value of the position is time independent. In fact, the expectation value of the position of the electron in the ground state will be 0. It cannot. Because for it to emit an electromagnetic radiation, it should be making a transition to a lower energy state. And since it doesn't exist, if it is in the ground state, there is no other lower energy state, it will not emit radiation.
Ortalama değeri oscillate ediyor demek ne demek? Yani ortalama beklediğim konumu oscillate ediyor. Yani nasıl, ortalama olarak nasıl oscillate ediyor? Hani atıyorum 3'te 1'in ortalaması, 4'te farklı bakarsınız, 5'te kendi yönteminizde ama ortalama beklediğim değerin oscillate etmesi ne anlamı geliyor?
Well, you see, now probably soon you will be seeing bird herds. They will be flying around. Okay? So it's a bad analogy in the sense that every bird in that group has a position. But the average position will be somewhere inside the group. And it will be moving. And it will be even oscillating sometimes. They just go to the left and to the right. They just fly around. So just like that, essentially.
Ama bir tane elektron var.
Yeah. Because we are talking about not, I mean, you see, the thing that is confusing you probably is still you are trying to think as the electron as having a position which you don't know. It just doesn't have a position. And how does okay, what does it mean it doesn't have a position? We all have a position now. But when we are talking about the position of classical objects or the macroscopic objects, what we usually talk about is the expectation value, because the probability distribution for a macroscopic object will be very sharp. So the most probable point, the most probable value will be the average value. But it just doesn't work when you go to the electron in a hydrogen atom. And when Maxwell says that every accelerating charge should emit radiation, he is actually talking about the acceleration of the average position. So that is the interpretation, let's say. Of course, Maxwell didn't know about this, but now how we interpret that result is that if the expectation value of the position of an object is oscillating, it should emit electromagnetic radiation. Okay. What do you mean by oscillating if the expectation value is always a constant? Well, you are still saying that electron has a position, so it goes from one point to the other point. That corresponds to this case. So in that case, it is emitting electromagnetic radiation. But that is not what an electron in the ground state is doing. Okay. How? Okay, so you are sending another photon. Okay. Okay. What do you mean? No, you are talking about the time average. Here we are not talking about the time average. We are not averaging over time. We are averaging over the probability distribution of the electron. That is mainly because, I mean, you see, if you just follow what we have been doing since the beginning of this topic, is first, the electrons do not have a position. We can only talk about the probability distribution, which can be described by waves. Well, what do you mean by how we describe it? Which wave do we use to describe the electron? Well, it depends on how you create it. Depends on how you create your experimental setup, more than how you measure it. You see, you can create a hydrogen atom in its ground state. Or in that case, there won't be any transition. Or you can prepare a hydrogen atom in the first or second excited state. Then it will make a transition. Well, let's see. Of course, there is a question is, what do you mean by when you look at an electron?
Wave function.
Okay. So you look at the wave function of an electron. Let's say, let me first write down these N, L, and M wave functions. These are the wave functions of an electron that has these three quantum numbers. And let's say that they are such that psi, N, L, M are squared, integrated over all volume is 1, which basically tells me that they are properly normalized. Now let's look at a given wave function. You see, these are the possible wave functions we can use. These are kind of the building blocks of the wave function of an electron in the hydrogen. Let's say that you prepare the hydrogen atom in some particular way, such that after your preparation, the electron wave function has this form. Well, let's say you picked up the hydrogen atoms. You cooled them. What happens when you cool them is they all go to the ground state, almost all of them. Then you send the photon whose energy is, let's say, equal to the energy difference between, you just shine a laser whose frequency just matches the energy difference between the ground state and the first excited state. So some of them will be excited. They might be excited, they might not be excited. So there's a probability of them being excited, probability of not being excited. So the wave function will be just the superposition of those two wave functions. Now, how do you create this state? Well, let's see. First of all, you have to also fix the angular momentum of the electron somehow. I don't know the experimental techniques that they can do that. Probably they will shine some polarized laser. But let's say that somehow our experimentalist friends prepared the hydrogen atoms in this state. Then what can we say about these hydrogen atoms, or when we make a measurement, what can we say? Well, first of all, what are the possible energies? Possible energy outcomes. You see, these psi and LMs are our building blocks, meaning that you can use them to write down the wave function. But for a given wave function, now this is our given wave function, it doesn't use all the building blocks. So not all the energies En's are possible over here. The possible energies are n is equal to 2, n is equal to 1, n is equal to 1. So the possible energy outcomes will be E2 and E1. For this electron, your energy measurement cannot yield any other value, only E2 and E1. Now, what is the probability of E2? Well, this wave function has the energy E2. Its coefficient is 1 over square root of 6. So this is the probability, 1 over 6. So if you have, let's say, 6 million hydrogen atoms having exactly this wave function, when you measure the energies of these hydrogen atoms, 1 million of them, in 1 million of your measurements, you will measure the energy E2. Well, what about the probability of E1? Let's see. It will be 5 over 6, but let's calculate it from here. Well, this wave function has energy E1. Its coefficient is I over square root of 6. The other wave function, the last one, has a coefficient 2 over square root of 6, so the probability is just its absolute square. So this becomes 5 over 6, as it should. Well, you see, this is the n number. This state and this state, they are different states. They have the same n value, and the energy is determined only by the n value. So those two states are what we call degenerate. These are degenerate. They are different states because they differ in the value of m, but they have the same energy value. Well, that is what we said over here. E2 and E1. You see, here we have three terms. This will give an energy E2, this will give an energy E1, this will give an energy E1. Yes. In the particular examples that we had studied before, all the n values were different. That was the prediction of the Bohr model. The electron was specified only by a single n number. But quantum mechanics now tells me that if you want to know the state of the electron, I have to know n, L, and m. Although L and m values of electrons can be different, if their n values is the same, they will have the same energy. So a different electron will have exactly the same energy. Well, at this level, it doesn't make any difference. At this level, there is no difference caused by the different values of L values. We will see them later on. But you see, at this is an approximation, let's say. At this accuracy of this model, there is no difference in energy due to L values. You see, here we are still discussing single electron systems. If you have more than one electron, things starts to get more complicated. Now let's see. What are the possible L-squared measurement outcomes? If I measure the total angular momentum, what will I measure for that electron? Well, let's see. That is our wave function. What are the different L values we have in that superposition? None. There's just L is equal to 1. So only L squared is equal to h bar squared, 1 plus 1, 2 h bar squared. For that electron, if I measure the energy, I get different values. But if I measure the total angular momentum, I get a single value in all the measurements. Well, let's see if they are all in the same direction. If they are all in the same direction, then all the LZ measurements should give me the same value, right? So what are the possible LZ outcomes? Well, you say LZ is given by m time determined by the m value. Well, let's see. The possible m values over here are 0, -1, and 0. Those are the two outcomes. These are the only possible values. Now, what are the probabilities? Well, the probability of having LZ is equal to 0 is this one. This has Lz is equal to 0, and this one has Lz is equal to 0. The probability of this wave function is, the coefficient is 1 over square root of 6. Take the absolute square. And the probability of the other Lz is equal to 0 is 2 over square root of 6. Take the absolute square. You see, now I am adding probabilities. And the probability that Lz is equal to minus h bar is just the second term, or the term in the middle. This has Lz is equal to minus h bar. The coefficient is I over square root of 6. Take the absolute square. One over 6.
It might be a stupid question, but like superposition, shouldn't we add the waves then find the probability? I mean, it makes sense to add probabilities, like, but why don't we add the wave? Like, think the wave as a three-part wave and add the waves to find the total probability. Why don't we do that in here?
You see, this is, we are adding the waves. And then when we are calculating the probabilities, how do we why do we just add the probabilities? Well, in fact, we are kind of doing both of them. You see, this is the wave. We are adding the waves. And in fact, if you would calculate the probability of the particle to be at the point R, probability density, this is actually psi of R squared. 1 over 6 psi 2, 1 minus 1 plus I psi 1, 1. 2, 1, 0, 1, 1 minus 1. Plus 2 psi 1, 1, 0 squared. Well, the distinction is basically, you see, it can be at the point R and be described by this wave. It can be at the point R and described by this wave. And it can be at the point R and described by this wave. So being described by this way or this way or this wave, they are consistent. They are all consistent with being at the point R. Let's look at the Lz is equal to minus h bar. Lz is equal to minus h bar and being at this way, and that's basically the only case. It can be Lz is equal to minus 1, then it cannot be over here and it cannot be over there. And let's see, what about Lz is equal to 0? How do we calculate the probability that Lz will be equal to 0? It can be in this one or in this one. Let's see. So probability of Lz is equal to 0. This is equal to, you are probably saying that, well, the superposed wave is this one. 2, 1, 0 plus twice 1, 1, 0. Take its complex conjugate. 1 over square root of 6, 2, 1, 0, psi 1, 1, 0. So this is the wave, as you said, a superposition. And And if you take the square, you get the probability. But this is not just the probability of having Lz is equal to 0. That is the probability density of having Lz is equal to 0 and at the point R. Now, what I'm interested in is the probability that it has Lz is equal to 0, no matter where it is. So I just sum all the R values. Well, let's see. I have 1 over 6 dV psi 210 absolute squared plus 4 over 6 dV psi 110 absolute squared plus 2 over square root of 6, the real part, dV psi 210 conjugate psi 110. Now, this will be the probability obtained from the superposition of waves. But you see, we had already said that this integral is 1 because psi 210 is properly normalized. This is also 1 because psi 110 is properly normalized. We didn't say anything about here. This is 0. This is 0. This is 1. The whole thing is 1. This whole thing is 1. This whole thing is 0. So it is 5 over 6. Well, you know the explicit values of psi 110, psi 210. Put the explicit values over there, you will see that it is 0. So actually we are looking at these superpositions. Now, we are looking at the transitions. At least one thing this tells us is that the transitions, the frequency of the emitted photon is given by the energy differences, also in this framework. And now, but there are some selection rules. Which basically will tell us that not all transitions, although they might be energetically allowed, not all transitions are possible. Now, we had looked at the expectation value of x when we were talking about the transitions. And we said that if the expectation value of x is oscillating, then we get a transition. But if the expectation value of x is 0, you see, if you go back, there are basically two things that determine the expectation value of x during a transition. Okay. This b, if we have a transition, this b should be non-zero, this constant. Let's go back. Oh, here I forgot some x's. So b is for b to be non-zero, okay, a and b, they should be non-zero. But if they are during the transition, a and b will be non-zero anyway. But there's also this factor over here. For b to be non-zero, this integral should also be non-zero. In fact, since the oscillation amplitude b is determined by this integral over here, this integral will determine how bright an emission line in the spectrum will be. If this integral is large for some values of Ni and Nf and small for other values of Ni and Nf, then in the case when it is large, it will be brighter because the amplitude is larger. So it's accelerating much faster in the classical sense. Then if it is smaller, it will be dimmer in the emission spectrum. Now, what are these selection rules? You see, this integral, well, if it's well, you see, if you go back, if b is non-zero, the expectation value is accelerating. It's not just changing; it's accelerating. It's oscillating. Where? Hmm? Where? No, that one. Yes, there's no x over there. You see, this integral well, we can just separate the various components. We have the r squared, this is the radial wave function for the initial, and the radial wave function for the final state, times r. Then we have the cosine theta, d phi, and x is cosine theta, no, sine theta, and sine phi. And then we have the theta wave function. This depends on L and M. Ni, Li. Then we have the phi wave function. It depends on, sorry, this doesn't depend on N. Li and Mi. The phi wave function depends only on the M. Then we have for the final state. Well, you see, the nice thing about this part is this theta function and the phi functions, they don't even depend on the potential you use. This potential might be different. You might, if you have many electrons, the potential might be even more different. But those terms, they will always be there, these terms. They will always be there. And that integral is, that part is non-zero only if delta L is equal to 0 or plus minus 1, and delta M is plus minus 1. Well, it's easy to see this one. Let's see that one. Delta M should be equal to plus minus 1. Now, if you look at the phi integral, d phi, you have the sine phi, this one is conjugated. Then you have the e to power minus I mi phi. Then you have plus times e to power I mf phi. You see, this is this term, this exponential is just this term over there. Now, furthermore, sine phi is actually e to power I phi plus e to power minus e to power minus I phi over 2 I. So if you put this over here, what you will end up having will be terms like the phi integral e to power I mf minus mi plus or minus 1 from 0 to 2 pi. Now this integral will be the sum of such terms with constant coefficients. Well, let's evaluate that integral. This is equal to e to power I mf minus mi plus minus 1 phi over I times mf minus mi plus minus 1 if f minus mi plus minus 1 is not equal to 0, if this is non-zero, then that integral will give me this one. But you see, this exponential function is periodic in 2 pi. So it just, when phi is equal to 2 pi and when phi is equal to 0, this exponential is just 1. Because this is an integer. 1 minus 1, it gives me 0. So the only non-zero case will be when mf minus mi, this is the change in m, plus minus 1 is 0. Only in that case, that exponential is 0. So e to the 0 is just 1. The integral from 0 to 2 pi of 1 is just 2 pi. So we get a non-zero number. So that's essentially why we have to have delta m is equal to plus minus 1 if we have to have some transition. And actually, from the perspective of angular momentum conservation, that also makes sense. Yes, let's say that you have an atom over here in an excited state. It becomes de-excited and just sends an electron in a photon in that direction. The photon has a momentum. The photon has an angular momentum besides the momentum. And the angular momentum of the photon can be at most h plus or minus h bar. So the component of, at least the component of the angular momentum of the electron in the direction of the photon should change by 1. It has to change by 1. That is actually this delta m is equal to plus or minus 1. So you cannot have a transition which doesn't satisfy these conditions. Well, you see, here we have an atom. Let's say the photon, when it's emitted, it moves in that direction. Let's choose our z-axis to be that direction. So initially, let's say the electron has an angular momentum in that direction plus h bar. The photon goes in that direction. The photon also has an angular momentum, and the angular momentum of the photon can be either h bar. Initially, the electron had an angular momentum in that direction with h bar. Then when the photon is emitted, it has an angular momentum in that direction, h bar. So the electron should have 0 angular momentum in that direction. So before the emission, it was at the state h bar. After the emission, now it has to be in the state 0, Lz is equal to 0. Delta m is minus 1. Any other questions? Okay, now we can give a 10-minute break.